Okay, everyone, thanks for calling in and joining in today. The next in our series of presentations from the core and NGD leaders is from Phil Jones, leader of the performance core group. So Phil, turn it over to you. Take it away.
All right, thanks everyone. As I said, we're going to be talking about what the performance group has been doing recently. Brief update here. So I always show this slide at the beginning of these presentations. These are the three goals for the performance group: kind of optimizing throughput for campaigns, preparing for future architectures, and creating the infrastructure we need to measure and monitor performance. But I think in terms of the first two, the future architectures are here, and we need to be prepared for them now. So those first two items are merging together. So as Mark kind of presented on Tuesday, a lot of these new machines are either on the floor or imminent. So Perlmutter phase 1 has been installed. We do have access through the NESAP program. Frontier will be delivered later this year, although users may not be able to get on till early next year. And Aurora is still expected in 2022, as far as we know. So all of these systems, they all have kind of similar networks. They're all playing with file systems to some extent. Perlmutter is going, for example, to all flash storage rather than spinning disk. But the important thing for us is that the nodes are all hybrid nodes, CPU combined with various numbers of GPUs. And the difference is that each of these machines is coming from a different chip vendor. So Perlmutter is a little more similar to the Summit in the sense that it's using an NVIDIA GPU. So CUDA is still the API for that. Or OpenACC and OpenMP directives can also be used. That's particularly helpful on the Fortran side. The difference is it has an EPYC front end to those NVIDIA GPUs. Frontier will be also fronted by an EPYC CPU, but it'll have AMD Radeon GPUs. Their API is called HIP, although they'll support OpenMP offloads as well. And then the Aurora system is going to be an Intel system with Xeons as the CPU and their new GPUs. And their API is called One API. Their ambition was to kind of unify API, but now One API seems to indicate that it only works on one system. So, but they will also support OpenMP offloads. So I guess the point is that these systems, at least early access, are already available. So if you were looking for the opportune moment to start working with these machines, now is the time. So as a brief aside, though, the current top machine on the top 500 list is the Fugaku machine. And we have been able to access this architecture, both Fugaku directly as well as some prototype nodes on other clusters, for example, at Sandia and elsewhere. So these are variations on the ARM architecture. It's called A64FX. It's somewhat of a custom approach in the sense that they've tweaked this architecture to try to make it a little more suitable for scientific computing. So we've run the home die core and performed some benchmarks here. Those results you can see on the right here. I guess the bottom line is it's behaving, I guess, a little similar to a GPU in the sense that it does perform well when there's higher workloads. But the performance, particularly on our benchmarks, isn't sort of outstanding. It's good, but it's still kind of modest for a new machine out there. It is good also in the sense that for a lot of these chips, you can actually adjust the power mode that the processor is working on, so we can actually run in a more energy efficient way on this architecture. So there are other custom efforts that we're tracking. There's one called Project 38. That's a DOE intelligence agency partnership. There's a partnership for some labs with NVIDIA for this Grace processor. Both of these efforts are really focused on high-speed memory and having a large, fast memory to try to get out around some of the memory bottlenecks in the system. But I guess the bottom line is none of these are going to keep us on the CPU track, and we still have to go down this hybrid path where we're working with nodes that have a mix of processors on them, from GPUs and tensor cores and traditional CPUs, as well as some memory subsystems. So these are going to be increasingly complex as we go forward. So as Mark presented on Tuesday, our strategy remains COCOS or YACO for the atmosphere, and then Peter is going to be talking about some of that effort on the next presentation. For oceanized components and impasse, we're using Fortran plus directives in the short term. A lot of that work has gone on under the ECP project, but we're merging those modifications into the current repo. There is a Ocean NGD project that's probably going to begin to transition the code base to C++. The API is sort of yet to be determined. We may stick with directives, or we may do something more custom. What we probably won't be doing is a COCOS approach due to some issues that we've run into with performance portability that I'll hope to get to at the end of this presentation as an example. The land model is also using Fortran plus directives. They're currently not a huge performance bottleneck, so this GPU version is used primarily for some of the very high resolution stuff they've been running for the North American continent. We'll also be using these new architectures for some more optimal use cases, things like trying out the multi-scale modeling framework and some of the highest resolution simulations. But I guess we're just about there in terms of being able to have most of the code at least running at some level of efficiency on these GPU architectures. So in the meantime, we've been working with the traditional architectures as well. So as most of you know, Chrysalis started exhibiting some performance issues after it was installed. A lot of this was tracked down to some bad network hardware, bad switches and cables, some configuration issues, both with the kernel and the software stack. There were some MPI bugs with the more optimal OpenMPI implementation. And then we found that hyperthreading was actually advantageous on this architecture. So fixing those problems and kind of tuning the model and configuration some, we're now getting 40 simulated years per day with the sort of standard configuration. So thanks to Oz and JS and the other folks at Argonne and with the vendors that sort of sorted this all out. We've been doing sort of the usual performance group work in tuning PE layouts on IO. We've been running in a lot of non-bit for bit issues and OpenMP issues that have arisen that we have to debug. Talk about that in the next slide a little bit. And then in another kind of side project, we've been there's been a long-standing wish to sort of replace the legacy CIs with MPS CIs in F cases where the older CIs model is still being used as the boundary condition there. So we finally did a performance study of that particular configuration, thanks to Pat Worley. And some of it was just configuration issues. It was doing a little too much IO, but some of the remaining costs are associated with the mesh and partition. So it's a little bit more expensive than running the CIs, but not prohibitively so, and there may be other things we can do here. So there are a lot of other kind of smaller issues that we continue to do. But I guess I want to do, you've sort of heard about this code review deep dive. So we're talking about coder integrity. And while there is no evidence of coder fraud, there have been sort of an increasing number of errors and things that have shown up. We're also in the process of adding a lot more in the way of taking in new development from projects across the DOE programs. So that's adding a lot more potential for introducing new bugs and new, along with the new features. We're probably not doing quite enough testing, especially in coupled mode. We're running into issues where things are showing up there. We've gotten into some bad habits with some absentee PRs where features are coming in through a back door. People are saying it's bit for bit because the option is turned off, and then when we turn it on, we realize there's some bugs. So anyway, there's just this general feeling there are gaps in process and in adoption of the code review process. So that's contributed to a delay in calling V2, for example. So we've set up this code review deep dive to see if we can improve this process for coder integrity, but yet not make it such a heavyweight process that it contributes to coder suppression. So we want to make it easy enough, but formal enough that we start to catch more of this stuff. But at least from the performance group's perspective, we'd like the opportunity to help you early on in the design of new features, because it's always easier to catch not only bugs, but sort of performance design issues early on. We also will need to evaluate performance later in the process to make sure it doesn't have a detrimental impact, or if it does, that it's justified given the physics we're introducing. And then increasingly, we're going to have to insist on code being GPU ready, or and things like OpenMP being sufficiently tested and that sort of thing. So that's going on. So you should watch out for what that looks like once we finish that deep dive. So as I mentioned, another thing the performance group does is create the infrastructure for measuring and monitoring performance. So a big part of that is gathering metrics, things like the standard E3SM benchmarks that we use to measure progress in this project. So we're awaiting the official V2 version before we rerun those benchmarks, but I think we're going to see some significant improvement in performance there, both due to our own efforts within the project as well as the improved hardware. We are kind of extending that effort some with there's a CP MIP project, and we have a proposed AG session to see how we can compare benchmarks across modeling groups, to sort of extend the kind of performance activities we're doing across the modeling domains. As part of our standard metrics that we typically gather, we've did some new memory diagnostics, and we've added more detail in some of the IO timers. So now we can do per file and per component IO benchmarks or IO metrics for reading and writing. In terms of IO infrastructure, we continue to improve support for audios, adding read capabilities and some of the seam support necessary to support that back end to the IO subsystem. We've contributed to the disk and file system policies on Compute to try to reduce the negative impacts of the full file system there. We've talked a lot about pace in previous presentations. We continue to improve, and that tool, the performance analysis tool, to begin to integrate some of the new IO metrics we're gathering and memory metrics. We're also adding some simulation context so that we can detect whether a simulation is part of a kind of a standard configuration, so that we can detect whether its performance is an outlier compared to similar simulations done with the same configuration. We would like to eventually get to the point where the tool is actually returning some performance recommendations. We are gathering enough metadata and enough model data at this point that we can begin to explore its use as a provenance tool to capture provenance for the model. So to some extent, some of the naming standards that are being proposed are going to help us to be able to search and provide context for all the data we're gathering on performance. So another thing we're doing, particularly for the machines that the program and the project own, is actually monitoring machine usage to see how well the machines are being used, whether we need to just update and queue usage policies. So as one example, at one point when we started monitoring this, we looked at Anvil usage and it kind of looked like this. So there is, everybody had been attracted by the new machines and Anvil was being underutilized. So that's an example where that's come into, that's been helpful. So we're evaluating a lot of other more performance specific tools, some listed here. But I wanted to go into a little more detail on a kernel extraction tool. I talked a little bit about this. This isn't kernel extraction in this sense or either of these senses, I guess. But I talked a little bit about this at the last all hands. So this is a tool formerly known as KGen or EKGen. We're now calling it IKEA. So it's E3SM kernel extraction and analysis tool. This is a tool that can extract a limited set of code so that we can do detailed characterization and capture enough of the realistic data that's feeding the kernel, so that's behaving the same way it would in a realistic context. So this is useful not only for us to do a real deep dive on performance issues, but provides a smaller code base that we can sort of pass off to vendors and see if they can improve issues that we uncover. So we've used that to do some detailed GPU characterizations as one example, but the example I wanted to talk about today is an impasse loop kernel example. I should mention that this kernel wasn't extracted using the kernel extraction tool, but this was a manual extraction, but just to demonstrate both the usefulness of a kernel as well as an example of the kind of performance activities you need to do to get performance on a GPU. So I always hate to show code, but these are two examples of a code extracted. This is kind of a common loop form that we encounter in impasse, where you're doing kind of a loop over either edges or cells, then you're kind of collecting fluxes across an interface to contribute to the cell or contribute to the edge in this case. So the code on the right is one that we had optimized for sort of traditional CPUs, where since a lot of the activity for this loop is occurring in the horizontal, we can push the vertical as the inside of the loop and we can get a vectorized inner loop. We can also take advantage of the fact that the number of vertical levels varies, so we can reduce the amount of work by doing a variable amount of work per column. We can also create some reduced size temporaries to improve the memory footprint and the memory access within these loops. So this is a pretty optimized CPU friendly form. Unfortunately, only the outer loop, if you put this in its current form on a GPU, only the outer loop is parallelized. So that doesn't give you quite enough parallelism for the GPU. So the code on the left is a little more GPU friendly. So we can push that K loop out over vertical levels and collapse the two loops. So that gives us a factor of 100 more parallelism, which is very effective on the GPU. We're no longer kind of restricting over the number of active levels, but that's okay since it's all being done in parallel. So you don't pay much of a cost for it. But unfortunately, this inner loop is a kind of a reduction, so it doesn't vectorize. And we can't do as many reduced size temporaries, so memory access times are increased in this case. So which again doesn't help you or it doesn't hurt you as much on the GPU because there's some high bandwidth memory there. So anyway, looking at these two forms, what we find is that the optimal GPU form doesn't work well on the CPU. We pay kind of a 50% to a factor of 2 penalty on when trying to use this form on a CPU. And when we look at the form on the CPU optimized form, we do get some advantage on the GPU, sort of factors of 2 to 3. But we can get a factor of 10x if we use a more GPU friendly form. So that's leaving sort of a factor of 3 to 5 on the table. So this is a case where it's becoming difficult to create a performance portable version. And that's why we're not sure whether a Cocos-like approach would work in this case. So these loop transformations are complex, so it's really not amenable to a common abstraction, though we haven't given up completely. And the fact that we've created this standalone loop kernel gives us a nice code that we can play around with, and we could try a whole bunch of different options and play. So in the short term, we're going to be retaining 2 versions. That's going to be kind of ugly for a bit, but we hope to fix that in the future. So in summary, I guess we're continuing to improve performance and keep the scientific campaigns going as best we can. We're building out our $2 trillion infrastructure plan. But the new machines are hitting the floor now, so it's really time for us to get on these GPUs. And so better, let's get at her for you Letterkenny fans. That's all I have to present today. Thanks.
Okay, thanks, Phil. There's some questions here. Let's start with the top. Chris, Golaz.
Hi, good morning. My question was, I think it may have been answered already, but is there any plan to make Pace open source like everything else we do on the project?
I can take that. So as I posted, so this is a public website. So we had some cybersecurity reviews associated with it at Oak Ridge. So we have been fixing a lot of things, and we just hired a new software engineer to clean up the code and make it ready for a release. For context, I mean, we can share it within the project right away. So we just need, I guess, for a public open source release, I want to catch any other cybersecurity issues before we do it. Because during the penetration testing, the red team, which actually was a cybersecurity firm, went through our source code and constructed malicious experiment packages to hack our website. So if somebody is going to go to all that trouble, I think we need to invest a little bit more effort into securing it before making it public open source. That makes sense.
Yeah, I want to add one note to that as well. We've talked about it with both performance and the infrastructure group leads that eventually Pace may still do what it's doing for performance, but a version of it will be taken over by infrastructure to maintain provenance for all the simulations, which is really more of an infrastructure role than one for the performance team, which has specific purposes. But the core engine and capabilities of Pace is extensible to that, but the specific requirements may be different. Okay, Rob Jacob.
I was just thinking out loud that this that case of the 2 loops might be a good one to experiment with a DSL with.
Yeah, and I guess that's a possibility. Like I said, some of the loop transformations can be kind of complex. So whether that can be automated or not, it's something we can still experiment with.
Okay. Andy Bellinger.
Yeah, I was just pointing out that you can, in Cocos and C++, you can have different versions for different machines, just as the same complexity of what you showed, not easier, not harder, I think, with template specialization. I know we have that in the home XX non-hydrostatic, and but you can always default to a same version, so you can get correctness and get code running right away, and then specialized as a second iteration through the code if you need to.
Phil, thank you again. Seeing no more questions, we'll ask you to close your screen. And
So,
Peter
Dave,
Cole?
my question may have seemed silly, but there is a real question in there about basically as code review gets more difficult, I'm concerned that young coders are basically going to have a really hard time.
I'm sorry, I missed
accessing.
it. Scrolled up. I'm sorry. Go ahead. This is a legitimate question. Go ahead. Sorry, Laura. I'm sorry.
No worries. So Phil, do you have any thoughts on basically how to make it a little bit easier for basically make the review process, if it's going to get more difficult in general, how to make it accessible to people who are kind of new to the project?
Yeah, I think so. There are a number of issues that go into that. I mean, so one thing we certainly need to do on our side is making the testing easier and more comprehensive to use. Some of the programming model issues and getting people coding in kind of the right programming models is going to take some training on our part. So that's just something everybody's going to have to spin up on at some point. But yeah, I mean, the issue is not to make this kind of this big onerous thing, but to try to put enough sort of gates in place as well as kind of help to get people through those gates as we can to make sure some of this stuff can happen.
Thanks.
Okay.
Sounds good.
Thanks, Zyler. And again, I apologize if your question scrolled off my screen. Is what happened. So, okay. Up next, Peter Caldwell talking about the model formerly known as Scream. Take it away, Peter.
All right. You guys can hear me and see my screen, right?
Yes, both.
Okay. Sounds good. Yeah. So the formal name of this next generation development project is the non-hydrostatic atmosphere project, but it's colloquially known as SCREAM. And so this is I don't know, a largish, I guess, NGD that we've also had a lot of help from people that are on other components of the project, like Charlie Zender, Rob Jacob, and others as well. So, so a lot of thanks to those. And so the acronym SCREAM stands for the Simple Cloud Resolving E3SM Atmosphere Model. And the simple part is because I believe that you shouldn't trust results you don't understand physically. So more complicated codes may give us more accurate answers, but actually stand in the way of making more credible climate predictions. And that simplicity is also needed because the SCREAM model is a complete rewrite of the E3SM atmosphere, which we need to do for performance, and more simple code is just less stuff to rewrite. So it makes it easier. And because we're targeting really high resolutions where we actually explicitly resolve a lot of processes, that allows us to use simpler parameterizations. You don't have to have as complex a subgrid scale representation. So in terms of the cloud resolving bit, I should note that we're not really cloud resolving in the sense that we have 3 kilometer grid spacing globally, 128 vertical layers, which is more than E3SM, which has 72, and a model top at 40 kilometers, which is lower than E3SM as well. So we're really zooming in on the troposphere. We have 50 meter vertical resolution in the boundary layer. So it's relatively high. And then finally, so SCREAM is planned to be the only E3SM atmosphere model by the time we get to V4 around 2028. And so at that point, the acronym is of course not going to be appropriate because it's going to be more than cloud resolving. It's also going to be low resolution. But for the time being, we have this acronym unless Dave bans me from ever saying it again. The other thing is that we should be able to do coupled simulations out of the box because the way that we're developing this connects with the E3SM coupler. And we have actually run a coupled simulation with 3 kilometer global resolution for I think a day, but we haven't analyzed it. So why would we go to 3 kilometer resolution? You know, this is almost 2 orders of magnitude finer resolution than we typically run E3SM. And the reason is, there are many reasons. One of them is that convection is the major driver of the tropical circulation. And we think that it's really critical for climate sensitivity, but it's really, really hard to parameterize. And so we're able to resolve the largest convective events explicitly when we get down to 3 kilometers. And that's kind of a real game changer for your simulation. So we think that it's important scientifically. This is also going to be really important for looking at climate impacts in certain regions because you can actually resolve them. So that'll be really important as well. And the other reason why this is a good idea is because the exascale computers that Phil was just talking about require more parallelism than we can get out of a conventional GCM run. And breaking the world into more columns is a perfect way to handle that. And so there is a trade-off here. It's really important to understand in that when you go to higher resolution, you're resolving finer scale processes that they have a shorter time scale associated with them. You need a shorter time step. So if you could afford to run, say, a million steps and your time step is 10 times smaller now, you're just not going to be able to run as long. And so a typical hero simulation with this sort of a model is probably going to be on the order of a year rather than centuries. And this is a little bit of an embarrassing situation when you're trying to simulate climate change. You can only run for a year. So that said, I think that it's not a huge drawback. I think there's a ton of things that we can do from short simulations. And in particular, because we know that clouds are the main source of climate change uncertainty, and clouds respond rapidly on the order of days to changes in forcing. And so therefore, cleverly designed short simulations should tell us a lot. And there are some nice examples of this already. And so one that I want to spend a moment talking about, because it's going to come up later as well, is so-called SES sensitivity simulations, which is shown on the right-hand side here, where the idea behind a SES simulation is that you run with prescribed SST for some period of time, years, and then you run the exact same simulation, but you increase the SST everywhere by some amount, like 4 Kelvin is typical. And you look at the top of atmosphere radiative imbalance change between those 2 simulations, and that tells you what the feedback from the climate system was, and in particular the cloud feedback, lapse rate feedback, and so on like that. And so this graphic on the right is just showing on the x-axis the SES sensitivity for cloud feedback, and on the y-axis the sensitivity you get from the full model. Each dot is a different CMIP5 GCM, and so you can see that for the most part you get the same answer whether you use several 100-year coupled simulation versus something like a 5-year SES simulation. So there is hope for these sorts of models. In terms of what's actually in this model, I guess I would characterize it as being higher resolutions / more advanced versions of what's in E3SM now. So radiation is the next generation of the RTMG package used by E3SM. It's GPU ready, that's what the P stands for. We have a non-hydrostatic version of E3SM's spectral element dicore. The microphysics scheme is somewhat different. It's the predicted particle properties, or P3 scheme, rather than MG2. Aerosols are just going to be prescribed in the initial implementation for simplicity. And there's a separate project called Eagles that's developing the prognostic aerosol for this model. And then turbulence and clouds are handled by the shock scheme, which you can think of as a simplified version of club. And of course, the whole point is to get rid of parameterized deep convection, at least. Shock is able to handle shallow convection. And we're also using the so-called PG2 coarser grid for physics and dynamics, which has been shown to make the model run faster without much impact on climate. So we have a two-pronged strategy for Scream. We've started out with what we call Scream version 0, which is just, we've extended E3SM to use Fortran versions of the desired schemes, so kind of prototype. And a major milestone for the project is that we've done a 40-day simulation, 3 kilometers globally, and submitted it to the Diamond 2 International Intercomparison of global cloud resolving models. And we've also written an overview paper about that. But I'll talk more about this milestone on a couple of slides from now. And so the main reason why we created this Fortran version is we want to use as a template for rewriting the code in C++ using the Cocos library that was described a little bit in Phil's talk just now for performance portability. And so this allows us to run the model efficiently on GPU machines, on CPU machines, and hopefully on whatever comes next. And the other major milestone for the whole project so far has been that we have completed the rewriting of the new die core in C++ and submitted a paper about it to Supercomputing 2020 and achieved really good results. And I'll talk more about that later as well. And so the major campaigns that we're working on right now is that now that we've done this simulation with the Fortran version of the code, we've seen some things that we want to improve, and we're working on doing that. And then we're going to do another 40-day simulation. So that's one effort. And the other major thing that we're doing is we're trying to complete the porting of the rest of Scream to C++ so that we can start runs on Summit. We're getting really close to that. And I'm hoping that we'll be able to start doing test runs on Summit around this August. And then another minor campaign that I want to mention is that we're creating a doubly periodic limited area version of the model. I'll talk more about that later as well. So I want to pause for a second and do some disambiguation because I think a lot of people are confused about what Scream is. And so Scream is just an atmosphere model. We have Fortran versions, we have C++ versions. We've targeted the parameterizations at 3 kilometer grid spacing, but you can run this model at whatever resolution you want. And in fact, we for the Fortran version, we're using it with a ZM convection scheme. We have a low resolution version that we use for testing all the time. So it's just a model. The second point I want to make is that a lot of people are going to be attracted to the Fortran version of Scream because it's we're used to it. It's just an extension of E3SM, but we fully intend to abandon that support for that version once the C++ version becomes fully functional, which is important for exascale ambitions. And so that should happen in the last year. So think twice before you start doing a lot of development on the Fortran version of Scream. And then I mentioned before, but the Scream code base is supposed to be the only atmosphere model in the V4 release around 2028. So lots of time to prepare for it, but expect that. So zooming in a little bit more on that first milestone. So being able to do that 40-day simulation with the Fortran version of the code. Operationally, we're getting something like 4 or 5 simulated days per wall day running on Core KNL. And I was personally shocked at how good the simulation looked in a lot of ways. And we're seeing an atmospheric river movie from that simulation on the right-hand side. And this was kind of a Hail Mary simulation. We did essentially no tuning at all. And so things looked really great. And so maybe we can say that, well, if you're willing to spend 1/3 of a million core hours for every day of simulation, that's what you get. some good looking results. And I mentioned before that there's some things that we're fixing right now. There's actually a preprint of our paper, goes into a lot more detail, linked here. So just a couple of other kind of eye candy slides about things that we're excited about with this simulation. So stratocumulus is something that's really hard to get in conventional GCMs. It's also been a challenge in global cloud resolving GCMs, and we tend to do pretty well. So this is a picture of the simulation off of the coast of South America, and so you can see open cells, closed cells, convection, it's very pretty. Our liquid water path looks just about perfect, or liquid water concentration. Cloud fraction is a little bit low, and we're working on fixing that. Another thing that's really exciting is precipitation variability. And so in particular, the diurnal cycle, which is shown on the left-hand side here, is amazing. So this plot here, of course, showing the tropics, and the different colors represent different times of day for the peak precipitation. And then the intensity of the color, the hue, is giving you a sense of the magnitude of the diurnal cycle. And so SCREAM looks almost indistinguishable from the CMORPH observations. Another thing that's really important is the Madden-Julian oscillation, which is typically looked at a graph like on the right, which is a Hofmüller plot. So what we have here is we have longitude on the x-axis and then time into the simulation on the y-axis. And so you see these bands of precipitation representing propagating bands of precipitation across, in longitude space. And so in this case, SCREAM doesn't look great in some senses, in that there's a lot more precipitation events in SCREAM than there is in observations. And this is one of the things that we know is a problem. We call it a popcorn convection problem, where we're just triggering precipitation too often. But that said, that the slope of the lines is just about right, suggesting that when we do trigger precipitation, we're able to propagate it in a reasonable way. So moving on to talking about the C++, which is of course our ultimate goal. I think we're in pretty good shape, I think. So all of our parameterizations are ported. We are able to do I/O. We are now working on just stitching all of these pieces together, and we're actually able to run for at least one time step, coupling everything except for the die core together. So that's exciting. We still need to read in some files for prescribed aerosols and greenhouse gases. And we've set up the coupling to other components, but of course we can't really test this working until we're doing full model runs. And so I think these things are promising, but you might be thinking, okay, well, it's going to take them 2 years to debug the runs once they get going. But keep in mind that we have been doing bit for bit testing between at least all of the individual processes in Fortran and C++. Our Fortran is looking really good, as I just showed you. And so I think there's pretty good odds that our C++ will work well out of the box. So talking about that second milestone of being able to do the non-hydrostatic die core, getting that working, writing a paper about it for Supercomputing 2020. This is just kind of the punchline results from that. I think that Mark showed this 2 days ago. But kind of the main punchline here is that if we use the basically the entirety of the Summit machine, so this is a GPU machine, you'll remember, and our updated results since the supercomputing paper, when we include semi-Lagrangian infection, is we're able to get 1.38 simulated years per day for essentially the die core only. And so remember I was saying that we ran the Fortran version for our 40-day simulation. We're getting 4 simulated days per day. 1.38 simulated years per day is really amazing, and it'll allow us to do more climate-like simulations. And I suspect it's also certainly for spectral element like die cores, this is the fastest result that anyone's gotten. So that's really exciting. Okay, so I wanted to move on for a little bit and talk about in detail about how the code structure works, which on one hand, it might seem like it's in the weeds, but also remembering that people are going to start to need to use this model when we get up to the V4 version. I think this is really important because this is how you're going to interface your model, your code development with Scream. And so we've taken advantage of the rewrite in order to use more modern software engineering. And in particular, each atmospheric process is a member of what we call the atmosphere process class. And so this is really useful because it makes code, each process becomes kind of an interchangeable block that you can add, reorder, things like that very easily. Also allows us to create tools that you can use on all processes. So that reduces the amount of code we have. And so beyond that, all of the processes are broken into first an interface layer, which is what handles all of the kind of Scream specific code and gets everything into a format that the individual process implementations can use in a kind of detail agnostic way that makes it easy to port these parameterizations to other models. Like if you want to run it in the GFDL model or something like that, shouldn't be that hard. And perhaps more critically, it allows us to do unit tests in a really easy way of these processes. And so that is really critical to our strategy. And then the other thing I should mention is that whereas in E3SM, at least for the atmosphere, you might note that there's something like 5 different ways that you can pass information into a particular process. And instead, in Scream, we have the field managers handling all variables. The only way to pass something in and out of the model is essentially, or in and out of a process, is through the field manager. So I mentioned unit testing, and that's something that I think is a really critical pillar of this project. So all of our C++ functions we've created, and we've broken down each of the parameterizations we have into a bunch of small functions. They all have unit tests. Most of those tests are just bit-for-bit tests between the Fortran and C++. But the thing that we're more excited about are property tests. So things like making sure that the process is conserving, that it's within the bounds you expect, that it's doing things right in limiting cases, and so on. And the graphic on the right-hand side is an example where we are able to find, by doing vertical convergence testing, a couple of different bugs in the shock parameterization that we were able to fix. Another thing that's really important for us is that we are using continuous integration to automatically merge our pull requests rather than having to wait. And I think this allows us to move a lot faster than E3SM, and that we can have multiple pull requests merged in a day. So that's worked really well for us. I did want to mention the doubly periodic Scream capability, because I think this is something a lot of people are going to want to use. So this graphic on the right is not from Scream. It's just an example of someone else's doubly periodic domain. So the basic idea here is that you have points that flow out one side of the domain just appear on the other side. This allows you to have a limited area to local version of the model, which is great for testing because you don't have to simulate the whole world. And so that's important. I should also mention this doubly periodic version is essentially an extension of EAM's single column model capability that Peter Bogenschutz and I have created. And so it has immediate access to the 30 or so ARM cases that have been documented for that. And so we think that this is going to be a great way for parameterization developers to efficiently develop things for E3SM, for Scream. So I think this is my next to last slide. I just wanted to mention a little bit more about sensitivity simulations, and something that I'm really excited about is Yi Chin in Steve Klein's group at Livermore has recently investigated the question of, okay, how long of a simulation do you need to use in order to get these sensitivity values? The traditional understanding is you need 5 years, which we can't afford to run. But what she finds and shows in this graphic is that after about 1 year, there's essentially no difference between the predictions you would make of sensitivity from coupled simulations, long-term coupled simulations, and a 1-year SAS sensitivity simulation. So based on that, it should be very possible for us to do these SAS sensitivity simulations with Scream. And so I'm really pushing forward to getting those done as soon as we can run on Summit. Okay, a little bit about future dreams, like what we might start doing for phase 3 of E3SM. Coupled simulations, I think, is a natural thing to do since we have all the tools in place. I think there'll be a lot of opportunity for, now we have a model, we can make it better. How can we improve the throughput? What can we do for performance? I think that we'll see ensembles of low resolution Scream simulations, also a good use of GPUs, more of a focus on science. I really think that the testing and code documentation is really important for having a credible, actionable model. Hopefully that'll become an even bigger pillar of our work. Regional refinement will be important, and hopefully coupling with aerosols. So with that, here's kind of a summary of what I think the take-home points are, and I'll just leave that up as I take questions. So, questions?
Okay. If it's okay with people, since we're short on time, I'm going to leave the discussion on what's the right name for this model to a later date. But if you want to look at the chat, there's all sorts of opinions and ideas about how this model should be named. So I'll just, like I said, leave that discussion for a later time. I don't really consider it all that relevant right now. Luca, I-core and single precision?
So is that a question for me or is that a question for Luca?
Well, I'm waiting for Luca to ask his question about I-core.
No, I was
Okay.
I was just pointing out that the slide said like the single precision offer a 1.6 speed up at certain point on a slide. I remember reading. We can run Scream and single precision, all the physics, but as of now, I don't think we can run home C++ and single precision. I think everywhere it's assuming or hard coding somehow double. So if one wants to try that in single precision ever, then that should be handled. Do modification or, run everything else in single precision and I-core in double, but we don't yet have that possibility.
Okay, sorry about that. I copied that from Mark.
Sarah has a further comment on mixed precision?
Yeah, so I think as Luca just commented there, basically the idea is exascale architectures would have better speedups for lower precision. So if there is a way for us to template or kind of incorporate mixed precision for different parts of the submodels, that would be great.
Michael Fraser. Oh, sorry, Peter, go ahead.
Oh, no, I was just going to say, I don't think that's a question, and I agree.
Okay.
Michael
Fraser, about model top.
Yeah, Peter, this is lovely, but if you really put if you run the top at 40 kilometers, you're going to sort of corrupt the stratospheric circulation. You can't really do a useful stratosphere. And that has implications also for the upper trope in terms of volcanism, aerosols, cirrus clouds, and so on. So are you planning on getting back to a little higher lid eventually? I understand why you picked that now, and it's reasonable to run with that now, but in the long term, if it's only 40, I think for V4 we'll be in trouble.
Yeah, I think your characterization is exactly right. That it's just temporary. Our focus is on the lower troposphere. So, and we want to really push the resolution as far as we can there. But yeah, for sure, for V4, we're going to have a higher lid.
Okay,
Okay.
may I ask a question? Because I put my question the first. So Peter talk.
Your question was about the name, wasn't it?
Yes,
Gotcha.
not really about name. It's about how we can accurately and consistently seeing the atmospheric model for V4. Because if we don't clarify that, that may cause a lot of
Yeah, I guess,
to me
like I
and
said,
DVD.
okay. I think we've pretty well clarified it in my first presentation. It's not the screen model at 3 kilometers, but the screen code base, the die core, the driver, and the physics packages all must use that driver that Peter described. That is the V4 atmosphere. It can be run at multiple resolutions. It can be run regionally refined. It can do everything the current model can, but it's written for exascale computers and can go to different resolutions and has more capability. Does that make sense? I don't think there's any confusion myself.
Yeah, that makes sense. But keep saying screen is the only atmospheric model for V4.
I think you're hung up on the word screen, and screen is not the current screen model is not V4.
Yes, so
that
that's
is being
why
developed for screen is
I
V4.
agree with you, Dave. So your description is accurate. Thank you.
Okay. And I think Peter said that too at the beginning of his talk. But well, like I said, I don't want to get too hung up in the labels and names and things like that now. But
we probably should change. Okay. We shouldn't stop using screen like the only model for V4.
Right. Well,
okay.
as many of you know, including Dr. Caldwell there, I objected to using the word screen when it first came out because I knew what problems it would cause later. But that ship has sailed, so they say.
Thank you, Dave.
Chi Tang.
Yes, I'm interested in that 1 year experiment can match the multi-year results. So we know there are longer timescale processes involved in the climate sensitivity. So I was just wondering how those does that mean that those longer timescale processes are not important in this SAS experiment?
Yeah. Well, so keep in mind. Yeah,
right.
I think.
Peter, yeah. Another question. Yeah, I have 2 questions. I didn't have time to put. So the other one is how sensitive that sensitivity is to the initial condition. So those are the 2 questions I have.
Yeah, those are great questions. So in terms of the longer scale processes, I think it's important to keep in mind that the SAS sensitivity, really it's the feedback, right? It's not like we think of equilibrium climate sensitivity or transient climate response as being, it's the feedback and the forcing. And so I think that it is true that the we're certainly leaving things off, and so the ocean response timescale and things like that, you're just kind of leaving out when you're just looking at the feedbacks. And it does, that scatter plot that I showed of the CMIP5 model shows that I think that you can, from short simulations, get a sense of the feedbacks, right? They're the atmospheric responses, and so therefore they tend to be faster. So not perfect, but for the most part. And then, so, oh shoot, now I've forgotten your second question.
To the initial condition.
Okay, yeah.
Sensitivity.
Yeah, so let's see. I guess in terms of, I guess I don't think that the initial condition is going to dominate even a 1 year simulation, right? We know that the chaotic weather effect is going to decorrelate you pretty fast. Yeah, I don't think the initial condition itself is that important.
Yeah, thanks,
Okay,
Peter.
moving on. 2 more quick questions. Let's start. Walter and Steve Klein, do you want to add on anything about the SAS experiments? before I move on to Matthew Hoffman, who will be the last.
Well, I can just put a general version of the question. About these test experiments, I was kind of wondering what the caveats were because I hadn't really dug into it. The question I asked in the chat was whether this applies to models with realistic land and seasonal variations, and Steve says it does. But I assume that you have to start with a spun up condition, so it's not like you can just take any old simulation, right? There's got to be some requirements, and I'm just curious what those are. Maybe there's some that are a little counterintuitive.
Yeah, that's a great point. And maybe that clarifies what she was asking better as well. That this plot that we're showing now was run by starting AMIP simulations off of the end of I think historical simulations or something, not the end, but they're not just spun up from scratch. If we did spin up from an unrealistic state, it would obviously take longer than a year to get things into balance. And so, yeah, I think that's really important that you need a reasonable state to start with. So I think that was part of your question. Was there another part?
No, I was just asking for any sort of caveats that you can think of.
Yeah. So I guess, so one other thing that I'll just quickly mention is that, so I think someone mentioned that things look, how do things look in the polar regions? We know there's a lot of more variability in the polar regions. So 1 year seems preposterous. And so Yi also made plots of the global maps of how long it takes to get reasonable correlation between the coupled versus these AMIP simulations that she was running. And I was really surprised to see that the polar regions didn't stand out as taking particularly longer than anywhere else. So that was a caveat that I expected that didn't seem to be borne out, and I don't understand why.
Okay, last question, Matthew Hoffman.
Yeah, you already answered it a bit. Just if you had any other comments about polar regions, in particular the distinguishing between liquid and solid phase clouds.
No, I guess, well, I think so empirically there was less difference than I expected. We do know that these ESS simulations, they don't, I think that they keep the boundaries of the sea ice at current climate conditions. That's of course weird, and as a result you end up with the sea ice feedbacks as being unrealistic. So that's a problem. But in terms of cloud phase, yeah, I guess you would expect, if you do a plus 4K warming, you would expect that maybe you keep the sea ice boundaries at current climate conditions, that you would expect weird things to happen. And so, yeah, these are definitely like kind of a crude sledgehammer sort of experiments rather than perfectly what you'd want.
Okay, Peter, thank you very much, and thank you everybody for the discussion. And I can surely the name debate will continue until the model's released in 2028 or whenever. Anyhow, as we move on, Peter, if you could kill your presentation and then Chris can bring his up, please.
Okay.
Thank you, Dave. So today we'll give you an update on water cycle activities. This is on behalf of both the entire water cycle group and actually the entire team behind the creation of the V2 model. So this is a very large set of contributors. And again, like in V1, we'll have a paper that lists everybody and gives proper credit. So the road to V2, everybody's probably wondering about what's happening there. So it's fair to say that it has been much longer and more torturous than we expected. We had a number of unexpected challenges that were discovered fairly late in the development phase and therefore caused unexpected delays. At this point now, we think that everything is in place. We think we have fixed all the known bugs, and we are currently running spin-up simulations. We're actually running 2 spin-up simulations with very slight different atmosphere tuning because we don't know yet where they will equilibrate when they fully spun up. And this is the time series. The green line is the fully spun up V1 model. This is the global mean surface air temperature. So the model was equilibrated and stable. And this is the ocean heat uptake in V1. And you see that it was also flat. So the model had equilibrated. The spin up simulation we're running in red and orange, they are still, the global mean surface temperature is still drifting, and the ocean is still taking up heat. So we are waiting for essentially the ocean heat uptake line to flatten out. And that will probably take a few centuries. And hopefully when we get there, we'll also have a reasonable global mean surface air temperature. There's nothing magical about this value. There's quite a bit of range there, but we want a reasonable value and something stable. But we know that overall, V2 will be faster and better than V1, which is a substantial achievement, given that models often from one generation to another become better, a little better, but usually slower and sometimes a lot slower. So achieving both faster and better is significant. Some of the lessons we learned from those delays is developers tend to be very optimistic people, and we love that enthusiasm and optimism. I don't want to dampen that down. So it usually goes something along the line, I have this great new feature, it's all ready to go, and it should really be in V2 because it's great. And sometimes that is the case, and sometimes it takes a little bit longer to get it all up and running, and sometimes a lot longer. So because of that, there is a plan to revisit the code review procedure to try to tighten it up without making it overly complicated. Another lesson learned is that there is something that I would describe as a delay positive feedback loop. You may start with a delay in one feature, and because of that, everything is taking a little bit longer than expected. That gives opportunities for B and C to, oh, maybe I can improve this a little bit more, or maybe I should revisit that. And then when A is ready, there may be a delay from something else. I'm almost there. And you can imagine that sort of develops in the feedback loop. It's not that easy to control because we want to be fair to developers, but we probably need to be a little more strict in terms of where to set the limit. So now coming on to the end result of that V2 development, we'll have not one, but two water cycle configuration. We'll have the low-res configuration with grids similar to what we had in V1, 100 kilometer atmosphere, 30 to 60 kilometer ocean. And that model is approximately twice as fast as V1. And this is comparing us on the same machine with a similar number of nodes. So this is really real. This is not just a better machine. And if you push the number of nodes high on the newest machine that we have, which is Chrysalis, you can go as fast as 40 simulated year per day. So this is really an awesome performance. I have to say that this is way beyond my wildest dreams. I was already ecstatic when we got to 25 years per day, and then 40 is just amazing. And this opens up a lot of possibilities. I mean, DOE is not interested in paleoclimate, but this is the kind of numbers that you could even consider millennium scale simulations. In 100 days, you could do thousands of years of simulation. We also have a regional refined mesh where the atmosphere is refined to 25 kilometers over the entire North American continent, and the ocean refined down to 14 kilometers as well. And this could be really an ideal mesh for a specific DOE application where we want a higher resolution over the US. And this resolution gets approximately 10 simulated years per day on Chrysalis. So if we compare to where we were in V1 we ran the simulation campaign with the low-res model on Edison, and we're getting 10 years per day. Now we can get the same years per day with the RM on a faster machine. So that's also a huge improvement. And then furthermore, we think that the RM produces a very similar climate outside of the refined mesh than it does in the low-res model. So the RM model can really be used as a full climate model. It doesn't have to be used in the nudge mode and just focusing on the refined region. So just a few selected results. This is precipitation bias. Green is too much precipitation. Brownish color has not enough precipitation. Comparing V1 to the model that is being spun up for V2. And you see that substantial reduction in the double ITCZ, that is much better in V2. The maritime continental excessive precipitation is improved, it's reduced a little bit. The Amazon dry bias is much improved as well. We also some improvement in the US continental summertime dry bias. It's not obvious in the annual mean. Excessive precipitation over high elevation is also reduced, and then overall the RMS goes down by about from 1.1 to 0.96, 15% or so. That is actually very significant improvement. This shows the seasonal average, the March, April, May season precipitation. That's a good season to look at for the double ITCZ. This is the observation. You see in V1, we clearly had a double ITCZ with what should be the SPCZ being zonal and going all across the Pacific. And then you see that in V2, the SPCZ looks much more realistic. It's not as zonal, and it doesn't extend fully across the Pacific. There's a little bit of hint here, but it's much reduced compared to V1. Huge improvement. The diurnal cycle is also improved in V2 compared to V1. It's not as dramatic as what we've seen from SCREAM, but it's going in the right direction. You can see from the color, they are closer to the observation that they were in V1. But the amplitude, I should mention, is too weak. We also have improvement at the top of the atmosphere. This is looking at the net radiation, which measures a lot of the cloud impacts. We have reduction in equatorial, Pacific, and Indian Ocean. You see the blue bias here, the negative bias is reduced. It's still present, but it's reduced. And there is also a substantial reduction in the bias over the stratocumulus region. So we have a lot of red in V1. This is not enough reflection from stratocumulus cloud, and this gets much better in V2. The pollen doesn't go away, but it gets much closer. And again, the overall RMS error goes down by about 1 in this case. But it's not just looking at the global picture. There's also process level improvement. This is the liquid cloud partitioning as a function of temperature. The black line shows the observation. As you mentioned, there's quite a bit of uncertainty on that line, so it should not be taken as the absolute truth. But V1 was here with a very unrealistic plateau here. That goes away in V2. So that's a significant improvement. And also we think we have more realistic partitioning at lower temperatures here. Something that we haven't really succeeded in making much progress was the AMARC, which was weak in V1 and continues to be weak in V2. We spent a lot of time and tried numerous things, including tuning, GM changes, changing the grid to resolve the entire Atlantic with a mesoscale eddy mesh, and nothing really proved to be robust. We found that MPAS is quite sensitive to the forcing in the atmosphere, so it's not just an ocean-only problem, it is probably a couple problem. And we had one unfortunate simulation that actually gave us a really, really nice AMARC, not perfect, but much better than anything we had seen before. But unfortunately, that was actually due to bugs in land feature. So sometimes model development is actually quite cool. You think you're there and then it's just a bug, and you have to admit that it's just nothing, it's a bug. Depending on how you look at it, you can see it was just a mirage, something that we saw in the horizon but we'll never get to. Or more optimistically, maybe it's the promised land. We will get there, but just not in V2. So that's the end result. This is the V1 AMARC. And this is the V2 spin-up simulations. And you can see they start nicely. And then they, over the first 150 to 200 years, they drop, and then they tend to equilibrate. and it looks like it's equilibrating at about the same range as V1. Okay, we have had a few simulations where it was going up again around 350 or 400 years, so maybe that will happen, but I will not count on that. There was a lot of work on sea ice and sea ice ocean coupling improvements. Steve Price will go over the details of those improvements in the next talk. Let me just highlight a few things. There's a dramatic improvement in the Arctic with an increase in the summer sea ice thickness. That was a major problem in V1. We're losing almost all the ice in the summertime, even in pre-industrial condition, and that is now much better in V2. Another improvement is regarding the Labrador sea ice. So the bias does persist at low res, but it seems to improve dramatically when we use the ocean refined mesh, the WC14 grid in the ocean and the sea ice. So we're hopeful that the RM grid will have a much better Labrador Sea. So E3SM is starting to become famous for its potholes, and by that I mean the lack of warming or even the cooling from the 70s to the 90s, and then the excessive warming thereafter. We analyzed that and we attributed this to the overly strong aerosol forcing or aerosol cloud interaction, and then the warm up after that to the large climate sensitivity. So for V2, we don't know what this will look like. We haven't done any historical simulation, but we expect that the aerosol cloud forcing will be somewhat smaller in magnitude. And then we also expect that the cloud feedback will be smaller, and therefore the sensitivity will be a little bit smaller. Is it going to be enough to fill that pothole? Probably not, but I'm hopeful that it will go in the right direction. In addition to a better model, we also spent some time trying to improve the user experience, which I think is very important. So some significant effort went into bringing back some sanity into the ComSet naming convention. This was really rather complicated, convoluted, and almost out of control, but nobody wanted to touch it because there was too much risk of breaking it. But Win bravely stepped into it and was able to do a lot of modification and simplification with the help of John Wolfe. So we won't have names like we had before, like AV1C04-P2, which probably nobody remembers what they stand for, but the A stands for either alpha or ACME, and then V1 and so on. And so definitely this was no more relevant. We also simplified the run E3SM script. There's continuing improvement in the diagnostic that we're using, advanced analysis, E3SM DAGs. We also have a new post-processing tool chain that we call Zippy. The eventual goal is to have something that we would describe as set it and forget it for those of you who are old enough to remember the infomercial. Other people can Google it. And the documentation, we also made a lot of progress there. There's a very nice run E3SM step-by-step guide. The goal is that eventually everyone who wants it and has an account on the machine should be able to just get the model up and running in about an afternoon. And eventually you should be able to do that on the Friday afternoon, start your simulation and come back on Monday and have all the figures and post-processing done. We're not quite there yet, but that's still my goal. Now, moving on to the simulation campaign that we are planning to do. This is still an outline. We haven't decided on all the pieces yet, but we're going to start with the deck simulation. So let's first start with the low res. That would be the full deck simulation, PI control, avoid 4 times CO2, 1% CO2, AMIP, as well as historical simulation. And because we have a model that is much cheaper than V1 was, and we also have much better computational resources than we did back then, I think there's an opportunity here to do an ensemble that is actually quite large. So we should certainly think about how large can we go? Can we even do a large ensemble ourselves with this model? And the idea would be to try to focus on DOE actionable science questions. We also have a plan to do a subset of the CFMIP and RFMIP simulation jointly with PCMDI funded by RGMA. And as that, like I said, there will be more added to the list. For the RM, I am hoping that we can actually do the deck. That would be quite an achievement. But since we're getting 10 simulated here per day, I think it might be possible. And then some of historical simulation, how large, I'm not clear yet how big we can go. Beyond the simulation, we are really looking for what we call simulation champions. So somebody come forward or a small team come forward and propose simulation, a simulation plan, and as well as paper or papers that they would like to write on it. We don't really want to just do simulation that sit there and nobody is interested in analyzing. So it's really important to have a consistent plan with somebody willing to do some of the work to crank the simulation but also analyze them. All right, so most of it was about V2. Let me just show you a few highlights of ongoing analysis on V1. And this is just a selected, this is not everything that is going on in the water cycle, but only 2 highlights to finish my talk. This is work by Kartik Balaguru, and this is under review in JGR. This is looking at comparing low-res versus high-res V1, and then the coastal SSE bias over the East and North Pacific improved considerably in high-res, which is a positive sign for the RM as well. This is related to the alongshore winds, and therefore the nearshore Ekman transport and the wearing are improved in the high-res. However, away from the coast, the SST bias is mainly caused by errors in the surface fluxes, which are less affected by changes in model resolution. So this might be a very good justification for using a regionally refined grid. Another work in progress by Qing Li, the paper is in preparation, comparing historical versus projection simulation for V1, looking at tropical instability waves. In the standard resolution of E3SM that tend to be better than other CMIP model. And he also compared the historical versus the projection, and then the strong tropical instability waves become more frequent in a warmer climate, as you can see from the PDF or the cumulated distribution function down there. And this is consistent with stronger ENSO amplitude in a warmer climate in E3SM. And that's all I had. Thank you all for your attention.
Thank you, Chris. There's one comment and one question, Rob Jacob, about changing the name of the code review process. You want to make your point, Rob?
Just that we're going to be doing a lot more than just reviewing code. You know, we're going to be looking at climate and performance. So we should probably call it the feature process or something like that.
Yeah, that's probably more accurate.
Xiaochang?
So Chris, it's very good to see the improvement in V2. I also want to add that actually we also found the MGO and the tropical waves got considerably improved in V2 compared to V1. So just for your information, my question is actually I'm curious, are the similar improvement in precipitation in the cloud also seen in atmospheric model only simulations? And any reasons for those improvement model retuning versus physical parameterization improvement? Could you briefly describe that?
Yes, so the precipitation improvement are definitely also seen if you just run an atmosphere-only simulation. In addition, we have something interesting that we don't understand is in V1, when you go from AMIP to couple, you get, not surprisingly, a degradation in the precipitation because you develop SST biases. But when we look at that for V2, we also get a degradation between AMIP and couple, but it's much smaller than it was in V1. So there might be something good about the retuning, or it's some other improvement in maybe the ocean that help us keep the precipitation better in couple. Most of the improvement comes from retuning the the various parameterization and the cloud and convection parameterization in the atmosphere.
Thank you.
Next up, Claudia was asking about scenarios.
I got my answer. Thank you.
Well, Luke, you want to speak your answer out loud?
Sure. So we will do a scenario, still debating between the 375 and 585 scenario. With the possibility of a larger ensemble, the 375 could be feasible for V2.
Okay.
Thank you. Okay. Who is going to decide at the end? I'm interested because I'm trying to develop a method that would emulate scenarios, but it would work best if I had two largish ensembles that bracket the space rather than one large ensemble only in the middle. So just curious about the decisional process here.
Well, you can, Claudia, you certainly can contribute to the discussion. I mean, that's what your mini NGD is all about, right? So since it's not decided, we welcome your input into that.
Okay, I guess I just send emails and anyway.
Yeah, so be careful what you ask for. You may just have to get involved. So, Zhijing commented that you know the delay. She's impressed with the computational performance and physical science. You want to go ahead, Zhijing?
Yeah, actually, the first time I to steer the presentation on the overall improvement of V2. So I think it's very exciting, especially the two sets of simulations. The second one, with some region refined mesh and deal with very kind of good computational speed. I think we're really moving step toward the addressing DOE actionable science. Will be a lot of kind of good applications. So that's great. And I know has been a very kind of much longer process, and use the case word is torturing or something, but I think worth the effort, and thanks everyone for your contribution. I think we're
Chris
there.
and Luke really got this done quickly because they were tired of me calling them up every day and saying, "Is it done yet? Is it done yet?" The kids in The Simpsons. So. Okay, two more questions. Matt Hoffman first, and then Walter.
Yeah, I was curious when the decision on the ensemble size for V2 will be made, and if you're willing to give any hints about how big that might actually be.
I don't. So let's say, so for V1 we did 5 ensemble member, which I think, looking backwards now, is ridiculously small. I think we can afford much more than 5, so it's going to be much bigger than 5. I think we need to benchmark the model in other, in particular on NERSC. We do have an allocation there. The model runs pretty slowly on NERSC, but if we can run 10 or 20 at once, we may get a pretty decent throughput. So that's something that will be done to evaluate how large we can go. If NERSC is a possibility, we may be able to go quite large. If we rely on Compi and Chrysalis, then I would say maybe 20 plus. But if we have enough time somewhere else, maybe we can go to 50. But those are really just guesses at this point.
Oh, those are all good numbers, so that's exciting.
Walter?
I was just wondering if you could elaborate on the plans for RRM, if we're going to do, like, if all this low-res simulations are going to be done with the RRM grid, or if it's has a different set of simulations that are planned to be run.
So we'll do both. Couple simulation with the low-res and with the RM in the atmosphere and the ocean. And the RM simulation will be coupled, and if we have enough resources, the plan is to do long simulation, including spin up, so the full deck, if possible.
Well, that's great.
Yeah, that's exciting. What you can do when you have a model that is faster.
Yeah.
And finally, Jiwen. will be the last question, and then we'll move on to the next talk.
Okay, can you hear me?
Yes, Julian, we can. Sorry to interrupt you. I apologize.
Yeah, I just have a quick question about your high resolution atmosphere model. Is that model tuned, or someone is working on tuning it? Because we really want to test P3 based on it.
That's a good question. So for V2, we made a decision to not emphasize the high-res atmosphere. So we don't have an official V2 high-res. Instead, we decided it would be more efficient to focus on the RM. We realized that when we were doing the V1 high-res simulation campaign, the model was just very expensive, and the simulation campaign is actually still ongoing. So we decided that for V2 to focus on the low-res and the RM. So there is no officially supported high-res.
Okay, thank you.
Okay, thanks, Chris. It's a great summary, and I think very timely, given that it's fairly hot off the presses with your new results. But I will sleep better tonight after saying that, so thank you. Next up, Steve Price, give me an update from the Cryosphere Group.
I will give an update on the Cryosphere campaign activities for the last year or so, and want to acknowledge Mark Peterson, Wu-Yin Lin, and the rest of the Cryosphere team who are all heavily involved in everything I'll talk about today. A quick reminder of what we're interested in. These are the V1 and V2 proposal science questions up for the Cryosphere campaign. So we're interested in the impacts of ocean ice shelf interactions on melting of the Antarctic ice sheet and what that implies for changes in global climate and eventually sea level rise. And we're also interested in understanding better how atmosphere, ocean, and sea ice systems mediate the sources of sea level rise from the Antarctic ice sheet over the coming decades. This year's efforts, we spent a lot of time working on new comp sets and configurations in support of a variable resolution Southern Ocean regionally refined mesh. We have new comp sets and new grid configurations that work out of the box to support that. We've done so far roughly about 150 years of simulation in the first iteration of that Southern Ocean refined mesh, which you can think of as we were running a sort of one of the pre-alpha configurations. We've done a little bit more than 150 years in the final version of that configuration, the R4, and we've basically been using that to shadow some of the water cycle simulation campaigns in their various tunings. So we've done Beta 1, Beta 4, RC1A, RC1C, the most recent one, and I suspect we'll keep on with that until we're at the version that water cycle is happy with. And that has given us at least a pretty good feeling of where we will be with our simulation configuration by the time water cycle is done with their tuning. We've also been keeping up running our more detailed polar analysis on most of the low resolution water cycle tuning runs, again, just so we have a better feeling for how that climate looks with respect to the things we're particularly interested in. Chris mentioned that Andrew and his team have made a huge number of improvements to sea ice coupling and heat and mass conservation. We've had some nice work from Shishon and Wu-Yin on new polar atmospheric capabilities. And while this was not originally in the phase 2 proposal, we have done quite a bit of work on trying to add a dynamic Greenland ice sheet component as well, mostly in collaboration with the SIDAC project. So I will come back to most of these things in a little bit more detail in the next few minutes. As a reminder of where we were, we're sort of at the end of version 1. Our goal there was really to be able to get realistic sub-ice shelf melt rates around Antarctica using a low resolution configuration. And we had this persistent problem where some ice shelves would, an instability would be initiated that would lead to a rapid doubling or quadrupling of melt. And that instability would eventually lead to roughly 2 times larger melt rates coming out of Antarctica than are expected or reasonable. So those are the red lines on these plots. Eventually, we discovered that with some tuning of the GM parameterization, we could fix that problem and get realistic sub-ice shelf melt rates. And those are shown here in the black lines. Now, this instability is actually, we think this is a real feature of the Southern Ocean and interactions with the ice shelves. So that's actually one of the more interesting science questions we want to pursue going forward, whether or not this instability is real and how it's initiated. But we don't expect that to happen in pre-industrial conditions, and that's the case where we were getting it. And that's all discussed in a pair of papers, one that we expect to be accepted any day now, and another one that's still in preparation. Why can't I advance? Okay, I guess I can't use the spotlighter. Okay. In the Southern Ocean refined configuration, I guess the big take home for sort of the V2 simulation campaign is that we don't see this problem. We have run a lot of different iterations, different configurations of this, using this Southern Ocean refined mesh, and we don't see this instability popping up in any of those simulations. So at least to this point, it looks like we're able to get fairly realistic melt rates, fairly stable melt rates under the Antarctic ice shelves without any additional tuning, simply as a result of the improved resolution around Antarctica. And there's a couple different ways to look at this. Here, I'm just comparing a V2 low resolution simulation on the left with the V2 Southern Ocean refined simulation. These are both exact same comp set, exact same tunings. And you can see that we just have much, much warmer water right next to the ice shelves and then probably lapping up under the ice shelves in the low resolution configuration. In the Southern Ocean refined configuration, we have a much more realistic looking temperature distribution at the ocean bottom, and particularly around some of these very large ice shelves, we don't have these warm water incursions that we were seeing before. If we looked at a plot of the seafloor salinities, you would see something similar in that the biases are much better at higher resolution than they were at low resolution. And another way to think about that, if we look at a temperature and salinity plot here, as you go down to the lower right on these plots, the water masses get denser. And what we have going on the shelf is a sort of battle between warm and dense water and cold and dense water. And if the water on the shelf is not cold and dense enough, then it gets displaced by very warm water off of the shelf, which promotes melting and leads to this positive feedback. So in our Southern Ocean refined mesh simulations, we're doing a much better job of approximating the water mass properties on these big ice shelves. And you can see that in these two plots on the right here. That red line sort of divides. That's the line where these warm circumpolar deep water masses sit on, and that's sort of where the density battle between these two water masses take place. Are people still hearing me, just to make sure my connection didn't die again?
Yep.
Yeah,
great.
we hear you, Steve.
Okay, thank you. Okay, so that's sort of where we are with the ocean ice interaction side of things right now. I think we're in a fairly good place to start our simulation campaign. Chris wanted me to spend a little bit of time ticking through the improvements that Andrew and his team have made. He went over the graphics already, so I won't go over those again. But there's so many changes. They take up 2 slides here. There was a frazzle ice formation bug fix that accounted for a global heat leak. The snow radiative transfer schemes over sea ice and land were homogenized. A new snow morphology over sea ice model was included. There was some bug fixes where the basal temp the sea ice and the ocean we're seeing were different, and that has been fixed now as well. The sea ice filtering has been removed that was put in place in V1 to damp some high frequency coupling problems. There was a checkerboarding issue associated with sea ice and ocean melt that has been fixed. The fact that ocean eddies and the eddy parameterization are the primary driver of the ice drift speed and the sea ice edge definition has been identified. And there's been a lot of work on analysis tools for diagnosing coupler inconsistencies. And these are basically the tools that were used to identify heat and mass leaks and fix those as well. In terms of the Southern Ocean, there are not a huge number of changes between the V1 sea ice and the V2 sea ice. The main changes are in the Arctic, but there are some substantial and important changes in the Antarctic as well. And that is, if you look in these 2 plots on the right-hand side here, those are V2 plots. You can see that, oops, sorry about that. You can see that there are areas around the coast in particular where the sea ice is thicker in V2, and those are important for deep water formation and interactions between sea ice and subice shelf melting and water mass formation. So those look like small changes, but they are actually important. I mentioned that Shishan and Nguyen have done a lot of nice work on improving our ability to look at the Southern Hemisphere atmosphere. The main interest here is in looking at a lot of different aspects of the southern polar climate that we don't have hadn't had tools to diagnose before now. In particular, things like looking at mean transports, large-scale modes of variability, southern annular mode, the Pacific South America pattern, ENSO, and how those impact things like surface temperature, winds, precipitation in and around Antarctica. So there's a lot of interesting graphics on the right you can't see the details of, but these are just some snapshots of some of the new analysis capabilities. Things that have already been implemented and tested and are available are diagnoses and plots to look at Southern Hemisphere large-scale modes of variability, polar jet stream, Hadley circulation, ENSO teleconnections, the polar vortex, and things that we're still working on are composites by polarity, weather regime analysis, and jet cloud radiative effects. If people have more specific questions on those, I'm going to refer you to Shishan and Nguyen during the discussion. Okay, I mentioned Greenland work towards a Greenland ice sheet component. That work has been happening in a number of different places, again, mostly under a SIDAC project with some help on the E3SM side from folks like John Wolf and Gautam. There we have a high resolution Greenland ice sheet model component that's being optimized to target quasi-equilibrium with E3SM climate. We've been working on adding new calving physics there that are appropriate for marine terminating outlet glaciers, and exploring some parameterizations that might allow us to have coupling between calving of marine outlet glaciers when that model is coupled to E3SM. There's been work on a new snowpack model in ELM that's more appropriate for ice sheet surface mass balance. We've done a lot of work in the last few months on some new composites and configurations to allow us to do surface mass balance calculations at higher resolutions, which we need to do in order to validate the surface mass balance component before we're confident that it's ready to go for forcing the actual ice sheet model. And lastly, we have started to be able to use a lot of nice analysis of the surface energy and the surface mass balance components using LiveKit. And I'll tick through just a few examples here. Some of the surface energy validation that we've started to look at. You can look at things like low, high total cloud content over the ice sheet, albedo, latent heat flux, downward and net long wave. These are all important aspects of summertime melt in Greenland. And you can see some comparison plots here and some bias plots. I'll note that these are coming out of a fairly low resolution, one of the first simulations we've done in E3SM using this new surface mass balance capability. So we don't expect these to be perfect. These are kind of our first cut to find out where we are and what we need to work on. And these tools are the things that we're going to be using to do that. Again, similarly with respect to validating surface mass balance, we can compare the actual surface mass balance to things like laser airborne altimetry plots down here in the lower left, compare with actual measurements of surface mass balance directly from ice sheet cores. And that's probably all I need to say about that. I mentioned we're doing some work on the ice sheet model side, and one of the interesting things that's come out of some of that work is we've discovered there may be a fairly simple parameterization for coupling calving rates to nearby ocean temperatures. About half of the mass loss from Greenland currently is due to icebergs calving from marine outlet glaciers. So while surface mass balance is more important to the rate of mass loss in Greenland than it is in Antarctica, the mass loss that comes from iceberg calving is still important, so we can't entirely ignore that. But one thing that's difficult is that the places where the ocean is in contact with the ice sheet in Greenland are much smaller than in Antarctica. We don't have these huge ice shelves that cover hundreds of thousands of kilometers. We have very narrow fjords, sort of 5-10 kilometers wide, that are going to be unresolved in our ocean model for quite some time yet. So there's definitely a lot of interest in trying to figure out some way to couple calving from outlet glaciers to the ocean without actually having to simulate that connection directly. And these plots on the bottom here are showing what some work by Trevor Hillebrand, who's a postdoc, he's discovered that if we force the ice sheet model for a particular outlet glacier to retreat according to what observations say it should retreat at, the mean rate of retreat over a decade, we find that there's a pretty strong correlation between that and the ocean temperature at the grounding line offshore. So there's actually this is not just a correlation is causation sort of parameterization we're talking about. There's actually some physics behind that I won't get into, but this is a nice, this would be a really nice way for us to have sort of a first cut at coupling between outlet glacier calving and ocean properties. Okay, so looking forward, I get this question a lot, when are we actually going to have ice sheets in E3SM? So the current timeline we're working towards is that by the end of phase 2, so sort of within a year or so, we expect that we'll have an operational Greenland ice sheet in E3SM. Sometime during phase 3, we expect that will be scientifically validated and we'll actually be able to use it during simulations. Also during phase 3, we expect that we will have an operational Antarctic ice sheet coupled to E3SM. And then at some point during phase 4, that should be a validated Antarctic ice sheet where we can start doing coupled simulations with E3SM and Antarctica. A few last comments here. Going forward, I just want to mention some things that we've talked about, maybe some areas for closer collaboration between water cycle and cryosphere during phase 3. There's a lot of interest right now in tropical polar teleconnections, and for the cryosphere campaign, this is really important. A lot of these connections are the leading cause of variability and long-term trends in the climate forcing that is actually impacting the Antarctic ice sheet and causing some of the dynamic responses we see today. There's also some important feedbacks between Southern Ocean climate and tropical climate that would be interesting to investigate. And another area I think would be interesting is looking at alpine water resources and changes. This would allow us to leverage some of the high variable resolution atmosphere land capabilities and some of the new surface mass balance capabilities and interest in glaciers on the cryosphere side for improving projections of changes in mountain glacier and snowpack evolution and looking at their impacts on water resources. So that's all I have. I don't know how I'm doing on time here, but Mark Peterson and Leanne Conlon had been working with a summer student at Lannel on making some movies, and while we were discussing, I told Mark I would play those movies, so I will do that now and just let them roll in the background while we are taking discussion and questions. So thanks.
Thank you, Steve. That was a great update. Lots of progress there too. So I see one question right now. That's from Chi Tang. Chi, go ahead.
Yeah, Steve. Yeah, I see a very nice, good polar dikes. So do you have plan to include the ozone hole dikes as the standard package in that whole set?
Yeah, I'm going to ask Wu Yin to hop in and answer that question if he's on the line.
Yes, Chi, and I think the ozone hole analysis will be included as part of the E3SM dikes. So either way. And because this one, whatever we do for the polar atmosphere analysis will be complement the E3SM dikes.
That's great. Yeah. So I have my own version ready, so we can implement together.
Okay, that's great.
Sounds good. Peter.
Yeah. So if I understood correctly, when you're talking about the problems you're having with V1 with the ice sheet collapse, that the solution was to change the GM parameters, and so I guess the question is that actually what you ended up doing, or did you end up switching to regional refinement so you didn't need to?
Yeah, so that is what we ended up doing in V1. And when our first look at low resolution V2, I think things looked so far off that we decided we were probably going to scratch any low resolution simulation campaign for V2 and just throw all of our resources into the Southern Ocean refined mesh. I think we'll probably take a second look at that now that we can, that we have. It looks a little bit better than originally, but I think we're still gonna press forward mostly with our Southern Ocean refined simulation campaign. And I should mention that we had just started poking around on Chrysalis to see what kind of performance we get there. And it looks like we're getting about 20 simulated years per day, which is more than 10 times faster than what we have been getting on Cori. So I will second what Chris said in the sense that, you know, there really is a whole new set of possibilities that open up to us with that kind of model performance.
Great.
Okay, Alan, you have a question?
Yes, Steve, I wonder about the bigger changes and improvement in the Arctic sea ice you mentioned on one of the slides. Is that also due to the better treatment of snow layers in V2?
That is a good question. I don't know for sure how much. You mean the overall thicker sea ice?
Yeah, you mentioned Arctic ice thickness is probably better.
Yeah, I don't have an answer for you on that. I don't know if it's more that or more just bug fixes or some combination of the two. I don't know if anybody else on the call has an answer for that question. Please jump in. I know Andrew is not on the call today because he had a family engagement.
Steve, this is Nicole.
Hey, Nicole, go ahead.
Okay, so I have looked at the sensitivity to the model by changing the number of snow layers, and it was very small. So I don't, you know, that particular feature is not part of what you're seeing here.
Okay, thanks.
Thank you.
Okay, Jill had a quick comment, and then the last comment I'll let leave to Zhijing. Jill, go ahead.
Oh, sure. So I'm very glad about the plan to incorporating polar diex into E3SM diex. It is generally a nice practice because for features that are interested by multiple science groups, it will be easier if we can implement these features in E3SM diex. Overall, it will reduce some overhead to maintaining multiple packages. So I really want to encourage that. Thank you.
Yeah, I sort of glossed over that detail, but for anyone who didn't get it, the current analysis package I was talking about is actually being done in NCL, and that decision was mainly made to get something in place quick that does what we need. But the long-term plan is that those same sets of analyses will make their way into E3SM diex. So we are definitely planning on going in that direction in the longer term.
Sounds great. Thank you, Steve.
Thanks.
Okay, Zhang, I'll let you have the closing comments.
Thank you, Dave. Yeah, it's a great update. I just want to thank all the speakers, Phil and Peter, Chris, and Steve. So Steve's performance group is really a very good plan for moving toward GPU and also more efficiently incorporate with other code developments. And Scream is very exciting, offer many opportunities, and Chris' presentation on the V2 improvement also very significant. So and Steve's presentation, yeah, the next step was very exciting. The water mass, I'm very impressed by the water mass improvement in V2 versus V1. Yeah, thank you so much, and thank you, Dave, for keeping everybody on track and moderating the presentations. So that's from me.
Okay, thanks
Dave.
everyone. We will see you next Tuesday at 8 a.m. Pacific, 11 a.m. Eastern. Bye-bye.